for joining us. You're here with Ryan Patton, Jesse Arnold, and Evan Stozel. This is our control system design project to control the pitch of an aircraft. First thing we'll do is take a look at our model. Our goal is to create a system that will control the longitudinal pitch of an aircraft. As input, we'll take the desired pitch of the aircraft in radians, and output the actual pitch of the aircraft, also in radians. This is the open loop block diagram of our system. You'll see that our plant has two components. The first is the actuator. This takes as input our desired pitch and outputs an angle to the aircraft elevators. The second component is the aircraft itself. This system takes as input the angle of the elevators and outputs the pitch of the aircraft. Here is the entire written out transfer function of our system. Again, it takes as input the desired pitch of the aircraft and outputs the actual pitch. Now there were a few assumptions that had to be made for this transfer function. First, our aircraft is cruising at a steady altitude and velocity. Also, changes in the aircraft's pitch angle do not affect the velocity. These adjustments and assumptions had to be made in order to make our system a little bit simpler and something that we could solve. Also, our system model is based on data from a Boeing commercial aircraft.
Now that we've defined the model, time to go over the plan analysis. Here you can see our transfer function again. Notice that we have 1, 0 and 6 poles. Here you can see the open loop root locus, but the dominant poles are kind of skewed. After zooming in, it's clear to see where the dominant poles are and that some of the gains are in unstable positions. Now we'll look at the Nyquist plot. You'll see that this is scaled back pretty far, so we'll zoom in to get a better look. As you can see here, we have a clockwise encirclement of -1, so this makes the system unstable. And as you can see here, our step response is unstable and increases exponentially. So as you can see, we've shown that there are two right-hand plane poles on the root locus plot, one clockwise encirclement of -1 on the Nyquist plot, and the step response approaches infinity. These are all indications of an unstable system. So the question is, what kind of controller do we need? We decided to use a proportional derivative controller because the proportional part will decrease the overall gain and the derivative part will add a 0 to ensure system stability.
Now that we've gone through our plant analysis, we will begin to design the controller. Here we have the design specifications for our controller. We decided on a rise time of under 3 seconds, a percent overshoot of under 20%, a steady state error of 0, and a phase margin of greater than or equal to 45 degrees. We, out of all these specifications, decided that the rise time is likely the most important, so as to keep the plane at a relatively normalized flight path so people don't get sick inside. Also, we looked at disturbance rejection to account for a wind causing a negative torque to the ailerons that would change the pitch of the aircraft. Here you see the closed loop block diagram, basically the same as the open loop block diagram, except now we have closed the loop, providing feedback in the system. Here is the closed loop Bode plot. As you'll notice, at the crossover frequency for the magnitude, going down to the phase plot, the phase margin is nearly 0, which definitely does not meet our specifications as is. Here you see the step response for the initial closed loop, and it gets worse and worse in its oscillations, approaching infinity.
Here you'll see the root locus plot where we have implemented some PD control. The first thing you might notice is that we added a 0 at approximately minus 0.7. Then we adjusted our gains for the dominant poles so that they were within our area of overshoot specifications. Here you can see the Nyquist plot for that same PD control setup. As was the previous Nyquist plot, it starts fairly zoomed out and you can't get a good idea of what's going on. After zooming in, we'll see that now we have one counterclockwise encirclement of the point -1. On this slide, you'll notice the Bode plot with our implemented PD control. From before, you might notice that our crossover frequency is approximately the same as it was without control. However, the big difference is on our phase plot. You'll notice that our phase margin is now approximately 45 degrees, which meets specifications. Now here is the output of our entire system with our implemented PD control to the step response. You'll notice that our rise time meets specifications and is less than 3 seconds. That our percent overshoot is less than 20%. And that finally our steady state value goes to 1, so our steady state error is 0. In conclusion, we were able to successfully meet all of our design requirements, except for disturbance rejection, which we have yet to test, through our proportional derivative control. We did this by adding a 0 and adjusting the gain in our root locus plot. This made our Nyquist plot have one counterclockwise encirclement of the point -1, which means it's stable. Now let's move on and assess our system's disturbance rejection capabilities.
Next, we'll move on to part 2 of our design, which is disturbance rejection. Here you'll see our new block diagram. You'll notice that there's been a torque disturbance added in the form of 3 ramp functions, which makes a ramp up and a ramp down that simulates a wind gust hitting the elevator of the aircraft. Here you'll see what the disturbance looks like. It starts at 0, ramps up to 80 ounce-inches, and back down to 0 in about 4 seconds. Here you'll see the response of the original PD controller that we found earlier to the disturbance. You'll see that the undershoot is pretty high, goes all the way down to -1.2 radians, and takes quite a while to go back to steady state.
Here is the optimized proportional derivative control to minimize the disturbance. If you'll notice, the undershoot value is about half of what it was before optimization, so this is significantly better. The settling time is still pretty long, but you can see that it does return to the original value, which is the important aspect. Here we have the step response using the controller values from the optimized system for disturbance rejection. As you'll notice, the overshoot is right at 20% and the rise time is very fast, and the system still returns to the initial value of 1. The problem with this model is that it would have somewhat of a roller coaster effect on the aircraft, pitching back and forth too quickly, so we continued to change the controller values to make it better. here is a compromise of optimization for the disturbance rejection and having a more realistic rise time. As you'll notice, the undershoot is somewhat worse than it was before. However, it's still decent, and this system is actually more realistic. As you'll see here, the overshoot is a little bit better, and the rise time is somewhat slower, which is actually better for the system since this is an aircraft with passengers inside. In conclusion, we were able to get our system to meet all of the specifications except for those set for the disturbance rejection. In order to have better disturbance rejection, it required a faster rise time and more extreme overshoot with a lot more oscillations. So to meet these criteria, we would probably need a more sophisticated controller and a more robust actuator. Sources.